Okay, I think we can slowly start. So I'm Stefano Marcantoni, I'm the chairman of this morning session, and today we start with the lecture of Professor David DiVincenzo.
Okay, thank you. So I will indeed just be continuing the subject that I began 2 days ago, and continue with, I would say, selections from these lectures on quantum electrical circuits. I've given a little bit more complete information now on the slide. If you wanted to see these, this is a book, but it's entirely freely available online from the Delft University Press website that's given there, or you could, I tried to figure out the shortest search string that would just bring you to this. Maybe there's a shorter one, but okay, now indeed this is only a selection, and but to remind you, the last time I feel I securely got you to this circuit and the idea that we know how to describe its mechanics, and also I indicated that we know how to describe its quantum mechanics, but I didn't really finish that yet. But let me give you a sort of map of today's lecture, and so here we are. So we've settled on this so-called transmon resonator coupled circuit as the one that will be sort of the core element of this, of what we do in electric circuits. You know, in other words, the fundamental building block out of which these kind of circuits are built. But I had a lot of choices, and this is only a map of what I might have done. And what I was going to joke, except Professor Sinha isn't here, is that if we had a good experimentalist who could set up for me a quantum random number generator, then I could have illustrated the many worlds scenario by, in the next hour, giving a lecture dependent on the outcome of the random number generator on any one of these branches. So that's the way you could have gotten the entire lecture, but I'm afraid that wouldn't have been so smart. And in fact, I've collapsed the wave function ahead of time. And I will certainly, for a chunk of this lecture, and this is maybe the most important part, if you want to remember anything from this lecture, is to complete the analysis of this circuit and to basically prove to you that it can do all the quantum mechanical things that you've seen in Pierre Rochon's tutorials, namely the basic, atom cavity coupling and all the tricks, all the beautiful tricks that you can do with that, state preparation and measurement and feedback eventually. There will be a theme also that which branches that there are other roads that can be taken with this circuit. So the circuits give other capabilities other than the Rydberg atom experiment, other than the Haroche, the Raymond Haroche experiment. Of course, that experiment can also do many, many other things, and there's a whole branch of new things that you do with Rydberg atoms. But there's a lot of alternative things you can do with electric circuits as well, and even this very small circuit has sort of tricks up its sleeve that have no analog in the atomic physics setting. And I'll be describing, I will spend time definitely on this branch of this many worlds diagram under the title of Cooper pair boxes and compactness. Unfortunately, many of those, although they were among the earliest ideas in electric circuit theory, cannot be realized very cleanly, and they instead uncover things about noise, about things that really limit the use of these circuits. But it'll give me an opportunity to extend my story a little bit of the formalism of this circuit. Now, the branches that maybe we won't travel, this is only the beginning of a many bodies story, many device. Even in this device, and I showed another picture of a 17 qubit device. There it is. There are now 1,000 qubit devices of this form, all assembled out of electric circuits. So some much vaster circuit than this is surely the one that describes that. And I'll try to at least allude to this. I don't know quite at what velocity I'll go in this lecture, so I don't know how far I'll get, but I want to at least give some hints of what the the extended circuit story has to be. And there's sort of two branches to that. There's the what I call the ad hoc way of doing this, which is the way it's mostly been done, of declaring that there is a good circuit and therefore a good Lagrangian or a good Hamiltonian for this. And then there's a more rigorous way, and that will maybe cause me to loop back to what is, for me, a kind of favorite part of this story, that this circuit, as I summarized, was based on a picture in the complex plane involving three poles. And I want to hope, maybe you can't even see that, but as I said, this circuit, or in fact, the part of this circuit to the right, excluding the Josephson junction, is very elegantly described as a three-pole complex function, analytic function. And so part of the story is to pursue this analytic function theory a little bit more into this many-body domain. Now, I'm pretty sure I will definitely not get to all of these branches, and in particular, I made a promise that I will not fulfill. I'm essentially certain, which is that there was a new measurement scheme that I described in my seminar lecture on Monday, and I'd love to give that, but that's only in some other universe, I think, or at the Blackboard later today, if anyone happens to be interested. Now, last time I got to this. Now, this Lagrangian, and I carefully argued what that's about, and of course that's only about a part of this circuit. So in a sense, I'm maybe violating this, the philosophy of what I emphasized, which that this circuit should be analyzed somewhat holistically, so I'm immediately not going to do that. And that's a little bit based on the fact that this capacitor, here C sub C for coupling, that physically this is often small. So let's take it to be 0, and we'll analyze the two halves of the circuit individually. Now, so that's the Hamiltonian, and now I didn't quite write it down, but I mentioned that what we want to do quantum mechanics, we want to do Schrödinger's equation for this, and to study both eigenfunction structure, eigenspectra, also driven versions of the system. So to do that, you do the Legendre transformation. And the only high point I want to mention to that is you need to identify a momentum, which is always identified by just taking the derivative of the Lagrangian with respect to the velocity. So this only one velocity in this, and that very reasonably gets the symbol Q, so it is in fact the circuit variable for charge, and that can be easily seen by actually doing this derivative and seeing that it's equal to the capacitance times the voltage. So this elementary circuit law emerges here as the rule for identifying the conjugate variable, and then the Hamiltonian is not at all surprisingly, I just want to write the correct constants here, Q squared plus, change of sign here, 1 over 2L phi squared. So in other words, the dynamics of a harmonic oscillator. And then finally, I sort of forbade myself last time from saying that I was doing any quantum mechanics, but now I finally do it. That is, we declare a quantum theory by elevating these variables to operators, to totally, first lecture quantum mechanics, and we introduce this commutator, and then we have quantum mechanics. And so, of course, there's basically hardly anything more to say here, except that it's helpful to, for the purpose of thinking about this, to go to some rescaled variables, which help us understand finally the mapping to this atomic experiment, to the Haroche kind of experiment. So let me just do this. And I will also, immediately, jump a few weeks forward in the quantum mechanics lecture, and we'll second quantize this right away as well. But to do this, I introduce a couple of energy constants. So there's a so-called charging energy, E sub C, and that's just the energy obtained by charging the capacitor with 1 electron. So a simple quantity. And then there's a energy scale associated with the inductance, which is, last time I introduced the flux quantum, the superconducting flux quantum. So this is now with some funny constants, and I can't justify for you at this moment where these constants exactly come from, but up to these constants, this is sort of the energy of an inductor if the amount of magnetic flux that its coil is producing is the fluxoid, is the 1 flux quantum. And then then you can introduce some dimensionless variables. So here's Q, which is the charge measured in units of not electron charge, but Cooper pair charge. And then there's a phi, which we'll call a phase, of course, which is this flux mechanical variable measured in units essentially of the flux quantum with an extra 2 pi. So I had a friend who used to say we need a phi naught bar in analogy to h bar, but that has not become a popular symbol, mainly because you wouldn't have any idea where to put the bar on such a picture, on such a letter. Anyway, so given that, the Hamiltonian assumes a simple dimensionless form, or a form where the energy, the fact that it has units of energy is very manifest. So 4EC Q squared, that's the kinetic energy piece, and then plus EL over 2 phi squared. Okay, so all of this is quite elementary. In these dimensionless units, the commutator of phi with Q is just I. H bar has disappeared because these are all dimensionless variables. Okay, so now I'd like to, let's see, where did I write it here? So now I'd like to introduce the second quantized description of this in using these new variables. So it turns out that you can consistently introduce boson, the creation and annihilation operators of this boson, of the bosonic mode of this oscillator, by writing phi. I see in my notes I start to put in hats, and I guess I should have started putting them in here. I don't know if I'll be consistently doing that. This hat is simply a reminder that that these guys have been elevated to the status of operators, and they're not just classical variables. So the identification that turns out to work is you always know that that a sort of position-like variable will involve this combination. This is a Hermitian operator, this combination of creation and destruction operators, and the same with the momentum, this other Hermitian combination of creation and destruction operators. And what you put in front, well, you have to work out, but it turns out that it's simple ratios of these energies. And I'm doing this because this eventually reveals, when you do this for both sides of this problem, this reveals the different regimes of operation, especially of this side, of this so-called transmon side of the picture. So it's this ratio, 2EC over EL, but that's not the end of the story, to the 1/4 power. And these, maybe you've never seen, they're always worked out quite specifically for the mechanical harmonic oscillator. And you don't see this sort of symmetry that it's just a ratio of energy scales and y to the 1/4 power. Well, that's how it works out. And then this one has a sort of reciprocal quantity. Indeed, it's EL over 2EC, and then again to the 1/4 power. Okay, there are a variety of other ways of writing this. Some revealing ones are in terms of the characteristic impedance of the circuit, of this LC circuit. I emphasized a little bit, or I was teasing you a little bit last time about knowing the meaning of this impedance has nothing to do with resistance, of course, but it is a quantity with units of impedance. And in cases where this inductor and capacitor is not literally I need to do this here, of course, is not literally, better seen here, not literally, a coil and a plate, couple plates, but if it's actually the response of a transmission line resonator, as it is in many cases in this circuit, then this quantity tends to be near the magic number that I mentioned last time, something like 50 ohms. But I won't develop that so much here. I mean, there are several alternative ways of writing these that reveal this and that, ideas about why the parameters are in the range that they are. It will be very significant identifying when this is much less than 1 versus much greater than 1, or much greater or much less than 2 pi, you might say, because it is a phase. Yes, first question. Oh, yes, sure. I was thinking it, and then I didn't write it. Excellent, yes. Otherwise, it would be not Hermitian, and it wouldn't be a good idea. But yes, indeed, that's the conjugate variable with the I. Thank you. Actually, then there's another minus coming up. So kind of cascading errors. So the overall sign turns out to be minus. That's, of course, less important than getting it to be Hermitian. Well, first was here, then Yuval. Yeah. Okay, that at some level is a very deep question. Why can we, we have these macroscopic things, these pictures are at the scale of millimeters, and I have this extremely big object with the billions of atoms, and why can I declare that it's quantum mechanical? And the answer is, well, it turns out to work, but the better way of saying it is that this is why we work so carefully at our mechanics. I don't say quantum, I just say we work very carefully to see if we have a system that's successfully described by a Lagrangian. And we think very hard about that, and we make sure there's not any other degrees of freedom, any other losses that appear, and that in the end, this, we do our best to establish that this is an extremely accurate Lagrangian for this system. And then the statement is we sort of have no choice. That is, once we introduce the quantum hypothesis, we say h bar is not 0, then nature has no choice. Nature doesn't have the choice to be classical. That is, if it says to you, I'm very lossless and I'm described by this Lagrangian, you say, okay, tell me your parameter values, and you may conclude that h bar is effectively 0. That's one possibility, that the quantum of action is so small that you'll never be able to see it. But if, on the other hand, you work out the energy scales. Now, okay, let me use your question to state one other important thing, that of course the quantum mechanics of this is that of a harmonic oscillator. Its eigenlevels are like this. The energy spacing is square root of 8 ECEL. So a nice energy. And if you work that out, and it turns out to be an energy scale that is actually measurable, for example, it's higher than your temperature, then you should expect, quantum mechanics forbids anything else. It says, okay, quantization is mandatory under those circumstances. And experiment shows that that's indeed true. Then you do spectroscopy on this. Sure enough, you see lines. Now, you get a complicated story that, well, for a harmonic system, it's a little hard to tell, actually. It's a little subtle. For anharmonic systems, it's easier to tell that you have a system that's successfully described by this ansatz, by the commutator ansatz. So sorry, that was a bit of a longish answer, but I don't think there's any shortcut to that. And yes, indeed, you could just say, I can't believe it. You know, we have billions of atoms. Quantum mechanics can't matter. And that's turns out to be a false line of reasoning. Yuval.
You mentioned that when you saw that the double combination of capacitors and inductors give you resistance, but this is not a real resistor.
Well, it gives you something in the units of ohms.
Also the real.
Pardon me?
And it's not imaginary.
It's real, yes, correct. Yeah, that's true.
So the question is that I can apply Ohm's law and following, they will tell me that there is some power dissipation there. So where is the power dissipation?
Nowhere. So the principle is that there's a concept which is not so popular in physics. I mean, I did a poll, you weren't here, but I did a poll on my first lecture and nobody remembered this. Of course, some lecturer tried to teach it, but you know, in the course of millions of other things. So you get to learn that the impedance of free space is 377 ohms. Now, it's not that, you know, when you send a plane wave through free space, it's not that it's sort of dissipating with some resistance involving 377 ohms. It's just that it's a characterization, it's a characterizing parameter, and even though it's a real parameter, it has the units of ohms, it does not by itself imply energy dissipation. Now, that's not really the end of the story. I can make a circuit, and I did in a previous lecture, where yes, you have 50 ohms and it's really, in a certain sense, dissipative, and that's the transmission line. That is a transmission line, well, I shouldn't spend too long on this, but a transmission line can be represented successfully with these circuit elements. You have a repeated ladder of inductors and capacitors, but it's important that it be infinitely many. So this is part of the idea that resistor has, you know, very, very many degrees of freedom microscopically. That's an important sort of principle of a resistor. These circuits have very, very few relevant degrees of freedom, so they don't at all they don't act like resistors in that respect. This device has infinitely many elements, and indeed, from some point of view, if you look at it from here, and you do experiments, you can't tell the difference between it and a 50 ohm resistor. You know, you launch energy into it, it never comes back. So, and indeed an unterminated transmission line, infinite transmission line, does actually look like a 50 ohm. Yeah. Right. Mm-hmm. Okay, in this example, okay, in the case of the small circuit, the power goes in, the power comes out. You know, it's just temporarily stored, but it hasn't been lost. It gets delivered back to you every half cycle if you're doing an AC experiment. So, but this one's special. If you launch it in, it would like to come back, but it's looking for the end. If it never finds the end, it never has a chance to reflect back and come back to you. So you delay the, you know, this is evidently not a lossy circuit, but it takes it infinitely long to deliver the energy back to you. So that's why it looks more and more like a resistor, whereas this does not look very much like a resistor. It looks like it very temporarily, that it sucks in energy, yes, but then it sends it right back to you. Are you talking about this one? Okay, if for the transmission line, that's true. It has nothing to do with the frequency. Whatever signal you send in, it just travels. It never comes back. In this case, well, it depends on the waveform, but you know, there is some trading of energy back and forth between this and you know, the thing that drives it, but the energy is never lost. Okay, very good. So now we're going to do a similar analysis. I think I had exhausted the whole story, and thanks for the questions. I think it's very illuminating to go through these things. Now I want to separately analyze this. I mentioned a few times, I should write it down. This is the transmon, but that's not the only name it has. It also is called the Cooper pair box. The Cooper pair box is an older idea, it turns out, and it sounds like it has something to do with, well, this is what's the box? Well, there's an actual metal island, which is like here, and you can say, well, is the charge quantized, and is there, is the physics that of Cooper pairs, moving on and off of that island? And in some cases it is. It just turns out to be not a good regime for doing successful qubits, which was painfully learned over years of research, but now this is history from 20 years ago. So now let me get myself to this next section of the analysis. I'm actually literally scrolling through and giving you selections from our book. This is page 16. I don't know if any of you have had the audacity to actually, pull it up yourself. Because then you could just be checking off, okay, he's saying this equation, he's saying that equation. All right, so let's do it this time. So now let me get rid of this one for a moment. Now I just have a notation question for myself that I think temporarily I'm going to call this C prime, because I called this C already. Unfortunately, when I go to chapter 4, they get some other subscripts, but I'm not quite prepared to get them all straight at the moment, but I'll be willing to put a prime here just to emphasize this is a different physical capacitor, as in general a different parameter value. Okay, but for the CPB, Cooper pair box, by itself, let's see, do I want to develop it all the way from the Lagrangian? Let's jump immediately to the Hamiltonian. So there's Hamiltonian for that, which is 1 over 2 C prime, Q prime squared. Because there's, the variables are, there's a phi here, and there's a phi prime here. And for the complete circuit, I will not need any more degrees of freedom. That is, all that will happen is I need to incorporate the energy of this capacitor, this coupling capacitor. So by writing these two pieces, I've got most of the answer already. Okay, now the Hamiltonian has that kinetic energy, and as I emphasized last time, has this sinusoidal potential energy, E sub c cosine 2 pi phi prime over phi naught. Okay, now that Hamiltonian, or what you say about that Hamiltonian a little bit depends more strongly, actually, on the parameter choices. That is, there wasn't much more to say here. That is, the formula, for example, for the energy levels is just true. It doesn't depend on whether E sub c is the larger quantity or E sub L, but that will be quite different for this case. Now, I put E sub c, that was wrong. I want a different symbol. This is not a charging energy. It's not exactly an inductive energy either. It's comes from other solid state physics, but it's still an energy parameter, and we call E sub j. Now, let me again rescale so that I get back to E sub c prime, and then this is Q prime squared minus, I don't change this is already a nice energy parameter, cosine phi prime. So in other words, the same rescalings that I've adopted here, and I could be doing hats everywhere, but that gets a little bit tiresome. But this is also a simple Schrödinger equation. And there's several ways to, but however, there's sort of two possibilities in discussing it. And I did say the word compactness, and so I will say it again. But it's definitely a problem in a cosinusoidal potential at phi prime equals 0. It's at a minimum, but 2 pi later, it's at exactly the same minimum, minus 2 pi. And it has exactly the same form of kinetic energy, just perhaps a different mass, but the picture is, again, just one of a massive particle in this potential. Now, in solid state physics, you would say, very beautiful. This is a Mathieu equation. This is a toy model of energy bands, because you have Bloch's theorem and you have plane waves, wave functions which have an overall e to the I k dot phi prime, and then times a periodic part of the wave function. And then there are energy bands, allowed energy bands, and forbidden energy bands, band gaps, etc. Now, that's not what we will say here, or it's not the majority view, although I wouldn't say that this is a completely forbidden line of thought. This is actually a subtle question of what's the Hilbert space associated with this operator. Is it all possible values of phi, a prime, or is it only bounded within one period? And there are good physical arguments for why the bounded is the right idea, because it comes from the fact that in the interior of a superconductor, this phi prime can be interpreted as the value of the order parameter. And then in there's a whole region of metal. One could actually go into the pictures and point out where that metal is, but where it ends is a very subtle thing, or hard to see, I should say, because the Josephson junction is so tiny. But you do see an island of metal connected only by tunnel junctions to the rest of the world. And you declare it's all superconducting, that's certainly true, and that it's small enough that it has one global value of the order parameter. This is not always true, but for a small piece of metal, this is a reasonable point of view that has a uniform value of the order parameter. It's in an equilibrium state for that superconductor. It's not being subjected to strong forces, so to speak. So it has a value of the phi, of the order parameter, but definitely from the point of view of superconducting theory, phi and 2 pi plus phi are not different. So that would argue that the Hilbert space is limited to this range, and so that you should view this as being on a torus. So that would imply that the energy spectrum is not what I was just sketching, because then, so you have to wrap the torus around, this line wraps onto itself. You identify minus pi and pi. And then the wave functions, it becomes, again, a discrete problem. And then with energy spacings that, this sort of the first energy spacing is indeed exactly this formula, except with Ej, square root of 8 EC Ej. And then the next energy level is almost that is the energy spacing, I should say the almost is already assuming a certain parameter value range. So I have to declare that immediately. So transmon regime is Ej much larger than EC. And this was not an obvious thing. It took some years, or there were some years of work on devices where these were of comparable value. And the main thing that was done to get into this regime was to make the system more classical. That is, to make C prime bigger. So you made the capacitor physically larger in order to suppress EC, and so that it was considerably smaller than Ej. So, for example, maybe 1/50th of Ej. Because now that really matters, and it matters due to the fact that this expression divided by 2 is also the 0-point energy of this. In other words, the distance from the bottom of this is 1/2 of this same quantity. And Now, if you are not restricting this parameter range, EJ and EC, this could very well be larger than 2EJ. This scale is 2EJ. So if it's larger, it's fine. It can be, the 0-point energy can put it up here with respect to this potential. But then it's not true that this will look even approximately like a harmonic oscillator. And in fact, it will look like another quantum mechanics problem, which is called the free rotor problem. And that has very different energy level spacing rules. The energy level as a function of the quantum number, index J, let's say, goes like J squared. It's a particle in a box kind of quantum mechanics. So very anharmonic spacing, and really have very little to do with the presence of the potential. And that is, in fact, the more of the Cooper pair box setting of this problem. And it was initially thought that that would be indeed a good setting. It's one where Q is almost a good quantum number. In other words, the basis states, which are eigenstates of Q, are the better picture in that regime, where the energy spacing is large. And so you have almost, quote, pure charge states, which in this representation, in this phi representation, look like plane waves. Okay, now this is all kind of a longish aside, because and I'll explain why. I mean, it's not so obvious why this isn't a good regime, and there was initial objections to this regime, but it turns out this is the far better regime to make a qubit than the Cooper pair box, and I'll get around to explaining it. And it actually is very much tied up with this compactness, the necessity of compactness of this variable. Okay, now in the transmon regime, the next energy spacing is almost the same. It's almost again 8 EC EJ. It's just a little bit smaller, minus EC, it turns out. So I'm summarizing, one could actually, of course, spend a much longer lecture working this out. In a sense, I will give a hint of why these numbers, when you get to the second quantization of this, you can see why this is actually the answer. So this is a little bit smaller, and then the next one's a little bit smaller still. I guess this is now 2 EC, the deficit is 2 EC. This is getting like a messy picture. But each pairwise separation from En to En plus 1 is a little bit different. And it continually shrinks as you go up this ladder. Now I say continually. Again, it's not really true forever. It can't be true forever. Let me kind of make a sketch about that. So more globally, so let me sketch this down here. Here's this characteristic of the transmon potential. You get initially this almost harmonic set of energy levels, and they start squeezing together. I realize that by sketching it this way, I'm in a parameter region where EC is even bigger than 50, EJ is bigger than 50 EC, because I'm about to draw something where you have really even more energy levels. But this very, very slightly anharmonic, and then there's a region where it's a little hard to describe. It's sort of not, yes, there are discrete energy levels, but there's no simple formula for them in this region. And then higher up, you get energy levels that are obey basically this square rule. So these spacings grow linearly. What do I mean by this? So the difference, let's see, yes, this will be like J lambda, J plus 1 lambda. We're already fairly high in the spectrum. So J, let's say, is the index. J is 1, 2, 3, et cetera. So and there's some other energy scale, which I'm not prepared to work out, but which is probably exactly EC. And so eventually the energy level spacing spreads out again, widens out again, but we've never seen that. This, however, is what's called the ionized region of the spectrum. Oh, I meant to meant to advertise that, of course, I am also trying to link together with the tutorial lectures of Benjamin Huard, who will be giving his lectures next week, who will come at this, of course, from a fully experimental point of view, but which will be very mindful of both doing justice to this as a qubit, but also going beyond and finding new capabilities for these circuits. Now, why, this was thought as really a bad idea when it was first surfaced. And I guess you had to be really well attuned to spectroscopy to realize this was not such a bad situation. What we say about why are harmonic oscillators not a qubit? Because, you have 0, 1, fine, you just stop, call that a qubit, right? Now, there are cases where that is in fact fine, but the trouble is the methods of control. So if you drive this system, meaning you apply some radiation to it, and you apply it in resonance with this transition, then indeed you will, the state of the system will evolve. If you start in the ground state, you'll end up in the first excited state, but there's nothing to stop you in a harmonic oscillator from exciting further up this ladder, because the energy spacing here is again exactly the same, etc. So it looked like that's almost true here, but it turns out not quite. That you apply this, resonant drive, the Rabi drive, and I'll comment in a moment what that means for the circuit. You should actually have a new element in your circuit to represent that. And of course, this Rabi drive is, so to speak, experienced by every level, but here it overshoots. So it fails to be in resonance. So you have the case of an off-resonant Rabi drive. Now, being close to resonance can indeed be dangerous, but there are choices of parameters. So the intensity of the drive and the duration of the drive can be chosen such that this is sufficiently far off resonance that it does not occur to any significant extent. So then you have, what it means is that you have at least the possibility of doing regular rotations on this 0-1 Bloch sphere and not getting level 2 involved, which would be leakage in the language of errors in error correction. Despite skepticism, it turns out that in this regime, even 1/50th EJ, that single qubit gates can be done with leakage error rates of I don't know what, but 10 to the minus 4. Pre-leak is something really small enough not to worry you too much. But if this knowledge, it's not an automatic, if some very eager student says, oh, I know how to do Rabi driving and it will be 10 times faster, and they just crank up the signal, say, yeah, sure enough, they've got the 0-1 going 10 times faster. However, the leakage rate's gone up to 5%. Whoops, okay. So, there are really dangerous sort of directions in parameter space in these circuits. So, don't let the students, I think none of you are the experimentalists, fortunately, so you don't have wild students going off and turning knobs in the lab. But this is a case where turning the knobs will definitely get you into a bad regime. I think nowadays these are, so to speak, forbidden in software. That is, if you use Qiskit, it's got all this knowledge built in, and you can't possibly, misdrive your qubits with Qiskit. I don't know, maybe Qiskit metal you're allowed to mess around, but there's a kind of layer of protection that's being built around these devices. So you don't even know all the hard stuff that's that's happening inside them. Okay, now let me second quantize, and that looks kind of awkward. That is, I'm going to use this just because, again, with primes, or I think I'll call these B's now. Now, you might say, well, that surely is not going to diagonalize this problem like it does for the harmonic oscillator. Of course, I didn't write the final equation here, but the Hamiltonian of the harmonic oscillator is, of course, just 1/2, again, square root of 8 EC A dagger A, plus 0 point energy. So just this simple number operator, fine. So it's, of course, not the case that this will go so simply. I'll put this, I'll do my best, I'll use the harmonic approximation to define the bosonic operators, and I can plug it in here, but I have a cosine of some funny operator expression, so not so handy. Now, what we do about that is we recognize that the desirable regime is indeed one where at least the lower lying states are not yet so spread out. So they're not, the wave functions of these will not extend to very large values of phi prime. You see, they're falling far short of this minus pi to pi. Now, you can see that it turns out here. Let me open up some space just to make a comment that this quantity also has the very informative name of, it's just a number, if phi ZPF, 0-point fluctuation. And it means that if you've written this out, this coefficient already tells you how wide this wave function is. So it is indeed, so it's a small parameter. See, I've said that we're interested in the regime EC much less than EL. So this is a number much smaller than 1, so confirmed. So the this extent of this wave function is indeed small compared with the full domain of this compact variable. Now, not by super much. Notice there's a 1/4 power here. So this, 1/50th to the 1/4 power is not very, very, very much smaller than pi. And that's related to the fact that I said over here that I was already sort of overdoing it. That is the actual energy level spacing, if you'll permit me to just put on a different thing. Now, this is for more, quote, realistic values of EC over EJ that are actually close to, where EJ is close to 50 EC. You get maybe 5 energy levels or so that are clearly in this harmonic regime. And then you enter this sort of cloudy regime where the next few energy levels you have no simple formula for. And then by the time you get to J equals, like 8 or something, then you connect on with this basically rotor point of view. It's not a sharp transition, but it's related to something else that I will now come to. Well, except I do want to sort of finish the story about the second quantization of this device. Let me just see, again, I have instructions to myself to jump to where, should still be around that page, okay. Yeah, I'm looking for the so-called Kerr description of the second quantization of this. I think I have to go to chapter 4, in fact, so that means I should go to around page 70, okay. Any questions while I'm getting myself ready for the next stage? No is a perfectly fine answer. And so yes, here we are. Almost. Yep.
Hello, sir. I have one question.
Yeah.
So this EJ is greater than 50 EC. This actually makes, I guess, less sensitive to the charge noises, and we have more flexibility to deal with inductive part of the Hamiltonian. I mean, that's what I understand. Is it true? I don't know.
Sorry, then I missed this point. What is so, or what is so?
So I'm saying that the range which you are talking, that EJ is greater than 50 EC. I guess this range makes the transmon less sensitive to the charge noises, and also it's easy to deal with the inductive part of the Hamiltonian, engineering point of view, speak. So I'm just trying to understand the reason behind this working range. Is it the engineering that is it easy to deal with the inductive part of the Hamiltonian?
I'm sorry, I have to confess, despite the attempt to improve the acoustics, my hearing, which is not so good, and your speech have not matched up yet. So I'm missing most of what you're saying.
So we can discuss later.
What?
We can discuss later.
We can do something. And I'm sorry, again, can't tell, but maybe we'll talk about it later. Okay, thank you. Yeah, we witnessed this last week with Michael Berry, and I have more or less similar problems as he, and I have less. I've used less tools for fixing it. Sometimes it gets me in trouble. I'm sorry. Okay, now I wanted to get back to explaining what happens if you second quantize. Now, okay, I guess I'll use my last clear part of the board here. So I just use the Taylor expansion of cosine. So second quantize. Cosine, well, phi, of course, is minus EJ. Okay, is minus 1/2, again, EJ out front. No, I'm sorry, it's plus 1/2. I'll forget about the constant, phi squared. And then I guess minus EJ over, I believe, 24, phi to the 4th power. And let me stop there. So I stop at 4th order. And now I plug in the bosonic operators. So I'll have here, instead of phi, I'll have phi prime. And I'll have B and B dagger here. And I'll have just the slightly modified formula here, just EJ rather than EL, but it's all completely parallel to this. That I get then that the Hamiltonian of the Cooper pair box is essentially H bar, well, it's called H bar capital omega in these notes, so I'll just state that in a moment. So it's B dagger B. So it's again, says first step of the description is that it's a harmonic oscillator. And then the next step is that it's H bar, I don't know why H bars have started to appear again here, so delta T over 2, but the important thing is it's just B plus B dagger to the 4th power, but then that indeed shows that this is not a good diagonalization. This will not give only quantities proportional to the number operator, or a function of the number operator. It'll, if expanded out, it will give B times B times B times B dagger, for example. And then you declare and you invoke a rotating wave approximation. To say those will not have the significant effects. You invoke some facts about perturbation theory, and you decide that the only thing that really survives is are indeed terms like this: B dagger, B dagger, B B. So those are. Well, and those you will also in turn treat in perturbation theory, but if you work out how it shifts the energy levels, it indeed shifts them according to the rule that I mentioned here, that the energy spacing is this, but it's decreased a little bit by this quartic term. And I guess a clue to this is that this delta T is indeed EJ. And this is essentially this square root of 8 EC EJ. If I do it this way, I get rid of the H bars, of course. So let me even not, or set them to 1, so to speak, or just recognize that I may as well just consider these as energy units. This with some small correction. So we do have, again, a kind of second quantized view, and I can also rewrite this as B dagger B squared, which makes it more clear with some rearrangement of terms that this is a way of getting a diagonalized description of this Cooper pair box, but in this transmon limit, where, and of course this Hamiltonian, I think well, yes, the notes say this is minus EC, and that's quite important, that this is indeed a negative term. It's obvious in the fact that the cosine potential turns downward, so it's less than the harmonic potential. Now, this is in fact a very pathological Hamiltonian. That is, if you take it seriously, it's the Hamiltonian of a potential like this. So, unbounded negative quartic. So you're pretending that there are eigenstates here, and yes, of course, they're sort of metastable states, but in fact, it has a whole continuum spectrum down to minus infinity. So this, in fact, a very singular description. It can work, and there are indeed, definite methods for having it work, but you just have to recognize that it has definitely very limited range of validity. It will not at all describe the actual spectrum up here, which is still discrete, as I've emphasized. Okay, now I wanted to get to what goes wrong, but actually a sort of interesting diagnosis of the physics of these things, and revealing about the types of noise, of problems that are present intrinsically in these electric circuits. So I said, where I just sort of made some kind of sketches and said you could do Rabi driving. Now, there is a legitimate way of representing that in circuit form, which is the following, that indeed somewhere in the outside world there is a voltage generator, V. So it's a new two-terminal device in my electric circuit description. So this is something which will have a voltage between the terminals, V0 cosine omega t, in tunable omega. And so you can couple it, and now it actually comes in, such signals actually come in through these signals. And if you trace what they are doing, they actually couple via some capacitance. So I call this C sub G for gate capacitance. And I could even zoom in and say, let's see which one. I think the green one, the green ones are the flux lines, drive lines. So the magenta there's a magenta drive line. It gets really close, and indeed, but there's a sort of capacitance separating it from the actual transmon circuit. So one can actually identify this as an element of the circuit. This is a little bit ad hoc from the point of view of my port theory, but it's a pretty good description. Okay, and so now what is this from the point of view of my circuit theory? Now I back all the way to my Lagrangians, and can I introduce, is it acceptable to introduce this into this Lagrangian formalism? I said that should only be a formalism that describes, linear, passive, time invariant elements. So this violates that on several accounts. But a voltage source, an ideal voltage source, is a pretty simple object. That is, it just says that, let's say, if the potential is, if the voltage is 0 here, it just says that here, it's indeed what I was saying, V0 cosine omega t, but let me just say that it's some function of t. So the voltage of time is just some function of t, which for a signal generator is sinusoidal. If it's an AWG, arbitrary waveform generator, it can be almost any function of t up respecting certain restrictions. Now, remember, we'd like to say things about phases. So there's a phi g here. This is a new node of this circuit, and it's a phi g. But phi g, observe, I'm doing classical physics again, is just a time integral of v of t. That was sort of the fundamental idea that defined phi, one of the fundamental ideas. It was first integral of v. So it's just some definite function of time. So it means this is not a dynamical variable. This is just a constrained quantity. in this dynamics, and it's constrained to be whatever this function is. So it's constrained to be a specific function of time as some sine omega t in the case of a simple signal generator. Now, so that's how you do drive. Now it turns out for, well, another interesting thing you can do that sounds rather more paradoxical is just to put on a DC voltage. Different symbol slightly here, you just say it's a battery. Now, that's a case where F is constant, but then in that case, phi g of t is a linear function of time, V battery times t. Now, that sounds like it's going to give us big trouble. You know, you have this diverging in time value of this phi, you know, and if this were appearing in some expression, if this were an inductor, for example, this would be a really difficult or problematic thing, because now the way you use this is you say this Cg does contribute to the energy in the usual way that capacitances do, but the and its contribution at the Lagrangian level involves the time derivative of the branch, you know, a time derivative of the difference of the phi's between this node and this node. So phi prime minus phi g. But time derivative. So in fact, I go back, I have to take the time derivative of this, so I can get back to a constant. So that means that it does modify the Hamiltonian, but in a very simple and acceptable form. Now you can trace this through the Legendre transformation, but I want to go back and point to here. So there's this, but it has an added term, but it's just a constant. So it's Q, and it's going to be still squared. So Q minus, I'm not sure if it has a name in this setting, but sort of Q offset is one language that's used for it. Just a constant, which is almost just this voltage. It's actually just Cg times V0 times the voltage of this battery. Now, it's been thought, and you might think this is in some sense related to what are called flux lines, but this is not a control that's any more used in these experiments, but it's interesting to inquire why. In the first point, or one point is it a control at all? Because let me remind you of what a term like this, how a term like this appears in normal quantum mechanics. You have recall you have momentum squared over 2m, but here it's modified. So it's p minus something, p minus, let's say, a squared, if that helps you remember where this appears in normal quantum physics. So it's the vector potential. So this is is behaving just like a vector potential in this setting. Now, however, it's a constant vector potential, and you probably know constant vector potentials can be gauged away. They don't produce any electric or magnetic fields, and so you can change gauge and make them zero. Not in a compact geometry, however. So let me give you a little picture. And I do have to make sure I leave time for the Jaynes-Cummings model, but this will come rather quickly once I say a few more things, but I wanted to get this picture. So I wanted to actually make a picture of this phi and phi prime space, but emphasizing the fact that it lives on a cylinder. Now there's no end to this cylinder, but it is wrapped around. So the phi prime variable is this way. The phi variable is this way. We have this vector potential. Now it's a vector in the phi direction, so it's, as a vector, it's wrapping around this way. But it's wrapped all the way around the cylinder, and that should maybe look familiar to those of you who know about, for example, Aharonov-Bohm effect. So it's, in this setting, it's equivalent to an actual magnetic field. I don't want to say flux, because then it gets too confusing, but I have a magnetic field which is proportional to this Q offset. And it has all the phenomenology of an Aharonov-Bohm effect. That is, if the integrated amount of this magnetic field is such that this is equivalent to a flux quantum in this funny, setting, then it should have no effect. And it turns out that the scale of this is E, or actually 2E. That is, if Q offset is 2E, or a multiple of 2E, it can be gauged away. Because it's equivalent to, the Aharonov-Bohm effect with full numbers of flux quanta. But if you're at some intermediate values, that's not the case. And yes. Okay, so phi, sorry, I've erased it already, but the phi was the variable, it's here. I'm writing it as the dimensionless circuit variable concerning the harmonic oscillator. So in this picture, the harmonic oscillator behavior is in this direction. So the state, the quantum state, is confined in this direction harmonically, and it has this cosine potential around the cylinder. And then in addition, this new degree of freedom, it has this additional vector potential that you can control by controlling an external voltage. Now, this usually doesn't have that much effect, and for the following reason, that now I'd like to draw on the surface of this sphere, I'd like to draw the wave function, so the ground state wave function. So it's pretty much a harmonic oscillator. I do it in the transmon limit. It's pretty much a harmonic oscillator, which means that the wave function is some Gaussian on the surface of this cylinder, and its extent in this direction is about this phi 0-point motion, which is much less than 2 pi. So indeed, it's just stuck on one little part of this cylinder. And then it has some also harmonic behavior in this direction. So it's basically also Gaussian in that direction. Since it doesn't wrap all the way around the cylinder, it is indeed not sensitive to this Aharonov-Bohm flux. So its energy is unchanged by n offset. However, that becomes increasingly untrue as you go higher in the spectrum, because excited state has some node here, and then it goes out a little bit further around this cylinder. And eventually the wave functions start to actually make it all the way around to the other side of the cylinder, and then they are actually sensitive to this effect. Now, it was thought, I'll say taking you back 20 years ago, that this would be a great control method for these things, and the original Nakamura experiments indeed used this in switching its value in order to control the system, do gate operations potentially. But it was a real struggle, and what has mostly been seen is that, what's seen in some very beautiful experiments, you work in regimes where this is not, well, you're high in the spectrum, or you take EC to be maybe 1/20th of EJ, so you're not far in this transmon limit. And then you monitor the position, say, spectroscopically of one of these levels, say this one. And as a function of time, so let's say level 2 can be, its energy can be monitored spectroscopically as a function of time, and you're not doing anything. You're not on purpose changing anything. And you see it does actually two things. It, first of all, slowly drifts. So it's a sign that, or a way of interpreting that is that this voltage, which is supposedly steady, is itself actually drifting in time. And that's considered to be a solid state effect, that there may be charged impurities and they hop around occasionally, and this is seen to have a kind of 1/f spectrum. So that's a real disaster for this as a controllable qubit. You have this intrinsic source of decoherence that's very intrinsic to the system. So it's far better to work in this regime where you're not sensitive to this flux. To this, fictitious flux, this vector potential. And so was finally the reason why one retreated into this Cooper into this transmon limit of this device. Now, I have just a short while to finally make the further connection. I've spent the whole hour and more analyzing only part of this circuit, because I still haven't said anything about this part, because finally these two circuits are coupled. And well, you might say they don't have to be, but there are many, many reasons why coupling it coupling the transmon to an oscillator is a good thing to do. Among them, you get all the tricks that were mentioned in the other tutorial series. But I can almost do it by, let me clean this picture up and bring it back to its original form. And you may have thought that I was just being very shaky or unclear, that I looked down on this and I said this is a Gaussian, but I didn't draw it very symmetrically, but that was on purpose. Because that is truly the effect, and in some sense the main effect, of the additional presence of this capacitance. So now I've got, unfortunately I erased part of this Hamiltonian, but I almost had the entire Hamiltonian. Let me maybe restore it here. I had plus EL phi squared. So the whole Hamiltonian is this, and this, and something else, but then with some modification, I have to say. That is to say, these have to be modified a little bit. It has to do with this non-locality that I advertised last time. So let me finally write the last part of the Hamiltonian. It'll be in this potential energy part, so it's actually common to, oh no, sorry, it's not. It is indeed not. So I have to say some things about the Legendre transformation. So I tend to forget, because once you second quantize, you sort of lose track, or it doesn't even matter very much whether the coupling Hamiltonian is of the charge form or the phase form. You still get basically the same kind of coupling terms in the rotating wave approximation. Okay, but the coupling is following my rules. I just say it's phi minus phi prime dot, so time derivative, velocities, squared, c sub c over 2. So that completes the story at the Lagrangian level. That's the entire dynamics of this whole circuit. Now, what this does give you is the Legendre transformation now involves this one further step that I alluded to last time, that if you assemble this into this two-dimensional dynamics and you identify this capacitance matrix, you have C here, C prime here, and then you have C sub C on the off diagonal. You also have it's also contributing a little bit on the diagonal, as you see. You square this out, you get some new phi dot squared terms, you get new phi prime squared terms, dot. But most crucially, you get phi dot times phi prime dot. So you cross terms are what introduce this coupling. The coupling is only in the kinetic energy, interestingly. And so you have to invert this. And that means that what you really need, you still get things of the same form, but this, actually, I maybe would put the tilde here in the sense that there's sort of an effective capacitance, but which is given by this inversion. In cases where C sub C is much smaller than C or C prime, then this modification is not very large. So these diagonal terms aren't changed very much. But there is finally a new term at the Hamiltonian level, which is, I'm not sure that I would get the right expression, but coupling at the Hamiltonian level in the Hamiltonian has the form, well, basically E sub CC with some accounting for the inversion, but it is proportional to C sub C, times Q prime. So it is actually a momentum coupling, and but it can be expressed in several different forms. It says that on this cylinder, that there is this sort of effective mass tensor, and it's not along the principal axes of the cylinder. due to this coupling. So it is a little bit rotated. That is the principal axes of this capacitance matrix. And so, if there were no issues about these boundary conditions, it would indeed be basically just the harmonic oscillator, in this new coordinate. But, well, because of several things, but largely because of this Kerr term, it results in a wave function which is indeed not separable. So, and it is sort of cocked in this funny way. But the further steps that you perform, let me now make a lot of space for myself. So, remembering everything that is being erased, the further steps are not that complex. You have E sub C Q Q prime, but for that you replace, I'm not going to get all constants right, but it's A minus A dagger times B minus B dagger. And then you can recognize that, well, the normal thing, again, using rotating wave approximations, is to say that the only, quote, important terms of this are A times B dagger minus A dagger B. So, schematically, what you're saying is that the physics of it is there's a boson that's hopping from one resonator to another. But then you further truncate. You say, because of all the arguments I gave, I will view which is the B system, as just a two-level system. And that will mean that, this using B dagger and B is sort of overkill for the two-level system. I may as well simply call that the raising operator in the Pauli algebra, sigma x minus plus I sigma y, minus A dagger sigma minus. And then I write this as G, and indeed I have the coupling that you've seen already, that is the sort of classic atom optics coupling that with which you can do many, many tricks. So this Jaynes-Cummings coupling. Now, indeed, just to make sure there's no loss of contact, I've now just gone to this quantum optics symbol, G, for the coupling, the atom-light coupling. But indeed, it has, indeed, I have it staring at me here. We have not at all lost contact with the circuit setting, in the sense that I can, and maybe I will, just so you believe that it's done and can be done, that G in energy units turns out to be E sub Cc. This is again going to be all in the limit that this coupling capacitor is small compared with the others, and if not, these are some not very complicated corrections due to the fact that you need a 2x2 matrix inverse. So it's basically set by the charging energy of this coupling capacitor, not so surprisingly. But then it has factors, so Ej over 2Ec, and is that the one I used the prime for or not? Yes, so prime, not surprisingly, 1/4 power, El over 2Ec, again to the 1/4 power. So yes, a complex formula, but directly bringing you back to the circuit theory. You have not at all lost the connection to the fact that this comes out of circuit parameters. And the job of the experimentalists has been to make this sort of as much like an atom as possible. So G of 50 megahertz or some number like that. They have their own target quantities, but they indeed can design to them by knowledge of the underlying circuit structure. And if they need, and I think it was somewhat pointed out in the very first picture, that you encounter situations where you say, because of the dynamics I want to set up, I want this capacitor to be rather large. And so you can't see it because of the pixel density is not high enough, or we'd have to magnify, but this is on purpose a much bigger capacitor than you would have had here otherwise. And it's to accomplish, not to tune in this case, the qubit resonator coupling. This is rather to tune up to ideal values the couplings involved in the measurement part of the stochastic equation. You want them to be of a certain strength. And that happens to be this, I've just happened to picked out this capacitor, and that's what this capacitor is doing. And so they figured out this needed to be rather larger. And it does, in fact, the actual G couplings that I'm talking about here are determined by specific details of this metal, little 5-pointed star and how close it comes geometrically to another piece of metal. So that has been, that's a design procedure that can also be done very rationally on the basis of this theory. Okay, now, as you've noticed, I've gotten about this far in this picture, and there we go. And so, of course, there's a little bit of time for discussion. I wonder if I can, maybe I'll say just one or two things. I have 3 minutes, and then I'll use it for one thing. I started by saying I wanted you not to forget the fact that this all came from a black box theory and a 3-pole, representation of this. Now, you can very reasonably ask, what about losses? And that's not a crazy issue in the sense that these are all resting on some dielectric. There is lossy, dielectrics have lossy characteristics, and so maybe that's an issue. And a thought was that what that would do is just move these poles a bit. So the rules of this is, loss means moving, having poles, just like we've seen in other talks. Poles in the left half plane mean actually loss. Poles on the axis, this is in the Laplace plane, mean no loss. And poles on the right-hand side are unphysical. They correspond to growing values. And that was indeed the basis of some discussion. Let me get to a little picture here. I think it's, yes. So for years it was thought, well, that means, or in some communities, it said, well, surely that means that I do this Foster thing. Remember, this is a so-called Foster representation. I don't know why I just did that. And you just throw in a resistor. Now, it's true that that would indeed move these poles. And that has been successfully used in some work at Yale. Sometimes they indeed have used this to describe this. However, it's an interesting aspect of the history of about 100 years ago. We were celebrating last year that quantum mechanics rose up 100 years ago. But it was discovered 100 years ago that this is false. That is that this simply adding resistors in parallel, will represent sometimes approximately the actual response of a lossy black box, but sometimes not at all. And this was actually sort of a crisis in this area of theory, kind of in parallel with the time of the crisis of quantum mechanics. And it was solved by this PhD thesis. So those of you who are PhD students, it still is possible to make major discoveries. This PhD thesis from almost 100 years ago by Brun, not the Brun in Harosh's lab, a different Brun, and he discovered a way of solving this problem. And that would be the basis of an entire additional lecture of how you really properly deal with losses, but it's also kind of connected up with how you deal with the many-body physics in a rigorous way for these multi-qubit devices. But that's all in a different universe that I gave that lecture. And but will stop now and be happy to have some discussion. But remember clearly and slowly. And as I said, I sometimes have a failure of understanding. So anyway, good.
Thanks. And any questions? There are microphones, different lines.
Yes, thank you, David, for the lecture. My question is about this correction to the junction potential you discussed last time, this 5% cos 2 phi.
Yeah.
And what is the impact on this overall picture of this new term?
Now I lost the last few words. Say it again.
What is the impact on this
Impact.
picture of this correction term?
Only very quantitative, I would say. I've unfortunately erased maybe the most relevant picture here, but it, I really took it away. Mostly, first of all, it just very subtly changes the shape of this potential. I believe it makes it generally more pointy. So this is a very much over-exaggeration. It's still a periodic function, but it's a little pointier. There's an asymmetry between here and here, which, I mean, there's no symmetry of that anyway. So it changes a little bit the shape, and it therefore changes the energy spacing of these intermediate levels somewhat, in ways that you can already see have to be there, but not at this level, but at the 6th order level of describing the junction potential. And that's what indeed was done in some experiments of the last few years, which were very painstakingly probing these levels and seeing that they wouldn't fit the conventional model. And my contribution to this was, I said, I bet we can make it fit if we put more poles in this picture. That is another resonant mode, and that turned out to be false. Okay, but that was at least a hypothesis to be investigated, that there was more resonant modes. But it turns out that the more compact and very compelling model is indeed that there are these small modifications of the potential.
More questions? Maybe I have one. So at a certain point, you mentioned that this operator phi, you have to choose the right Hilbert space for the operator, and you choose the compact one, the torus.
Yeah.
So, but do you have any, say, reason to, or any way to distinguish between this choice and the other possible choice?
Yeah.
Or
well, I know some workers who believe that that what is going on is that the Hilbert space is non-compact, but there are some selection rules in operation. And maybe even that this story that I told here is not the interpretation I gave you, which was this business of actually changing the boundary conditions of this compact space, but rather some kind of forces or something that violate the selection rule and actually take you into other parts of the Hilbert space. But I haven't seen a compelling full story of what that would really mean. So no, I don't think I have, I mean, then you might say, well, it's a somewhat philosophical question, or you just say the compact model fits most features of the experiment very well, so we stick with that. So it's based on appeal to experiment. Yeah.
Can you say a little bit more on oscillatory drive? Here you detail constant drive.
Yeah.
And the difference with oscillatory drive.
Okay, well, so it works out. What I mean by that is that you replace this battery, or you have the alternative of having a simple sinusoidal temporal drive. So what this theory says is the way it goes into the construction of the Hamiltonian is you do a first time integral of that, but okay, no big deal. You change a cosine to a sine. That goes in and makes a time-dependent Hamiltonian, which indeed appears here. So it becomes a time-dependent offset, but this is indeed a setting where, okay, with just a few more steps, think second quantization, it means you square out this, so you get something linear, linear in the this operator, so think a plus a dagger, a minus a dagger, times cosine, times sine omega t. So that becomes then the totally conventional setting of what you mean by driving an oscillator, say.
Thank you.
No, just coming back to the question of like why we are allowed to suddenly quantize the. So I was wondering, like, is it possible to think of like a more microscopic picture where we consider the electromagnetic field in the cavities, and then they are interacting with the superconductor in. So I could write a microscopic model, and then it's just the quantization of the field.
Yeah, I think for the pure field problem, yes, indeed, you can do all that. Actually, the subtler one is the problem of the Josephson potential starting from microscopics. I would say, as a general fact, you can always, one can be assured that this is all consistent with a theory with many more degrees of freedom. In the case of the electromagnetics, it means you should do the quantized electromagnetic field. But then you find that has many degrees of freedom that are completely frozen out. So you have to go through some reasoning of why they're frozen out and why only a very few of them are still active. One mode remains sort of active and becomes part of the low energy description. So that can be a very arduous derivation. I think, we feel it could be done, but this sort of shortcut has been very successful, where you come to the low energy degrees of freedom by some reasoning, which says, well, classical physics would be perfect for this, and then you reason of what degrees of freedom that would give you, and then you say, oh no, but the world is quantum mechanical. Now that's been a successful, this sort of re-quantization. Even weird ones where your classical theory itself contains the parameter h bar. That's a really strange one, but is understood again in the theory of Josephson tunneling, of why that gives a sort of semi-classical thing that you then reason about further and then re-quantize.
So why not inductive
I have
coupling?
a question.
Why not inductive coupling?
Why not what?
Inductive coupling.
Why not? And I heard something coupling. I'm sorry, I just have trouble hearing.
Why not inductive coupling?
Inductive coupling, thank you.
That
is
more
done.
natural to me.
Okay, yes, that is done. And actually, you can read a section of our book where we indeed study this circuit, which has sometimes been used. So you have this, and you have this, and then you have what I haven't introduced, which is mutual inductance coupling, but that's also straightforward from this energy formalism to include. I think the reason it's not done is it's just more straightforward to make capacitors on chips than inductors, and especially to get mutual inductance is very awkward on chips. Nevertheless, there are systems where it's done, and actually the D-Wave computers use inductive coupling. They use a different kind of qubit, very less coherent qubit, but still one that can be described with circuit theory, the so-called flux qubits. So yes, it could be done, and no, it isn't done in any current, definitely no, never in any sort of transmon-based devices.
I had one question.
It's online.
Oh, online, okay.
Yes, no, this is actually connected to the issue of quantization. I was just wondering if one remains in the low temperature regime, where delta E is much greater than KBT, so to speak. So quantization is justified.
Yes, okay, so indeed that is an aspect which maybe I said extremely briefly, that when you come to the, okay, I'll sketch again things that have disappeared. These theories make definite predictions or statements about what these energy spacings are. They are indeed quite a bit larger than KBT, where T is millikelvin, 10 millikelvin or something. So indeed, from that point of view, yes, these are in that quantum regime. So it is indeed achievable. Sometimes you have devices which aren't kept cold, and yet you can still use this description, but it's because you can cool specific degrees of freedom. That's been occasionally done in these electric circuits, but it's more done in atomic systems where with laser techniques, you cool specific degrees of freedom to very low temperature, even though the device is at ambient temperature.
Thank you.
Welcome.
Okay, I think we can thank Professor DiVincenzo for this lecture and for all the lectures that he gave us.